Right now, somewhere in the world, there's a cup of coffee sitting on a counter going cold. They poured it hot. The steam rose. The heat spread into the air around it, and it will never, never spontaneously get hot again. At least, I certainly hope not, because that would be weird. Suddenly getting hot again isn't a limitation of your coffee, it's a limitation of reality itself. That cooling cup of coffee is doing something the entire universe is doing. Winding down, spreading out, moving relentlessly toward a state where nothing interesting can ever happen again. The stars will burn out. The black holes will evaporate. Every atom will drift so far apart that none will ever touch another. There will be no heat, no light, no life, no change, just stillness forever. Physicists call this the heat death of the universe. And it's not speculation, it's where the second law of thermodynamics ultimately leads. But I should be precise. Heat death is the leading prediction based on our current understanding of dark energy. If dark energy behaves differently than we think, strengthening over time, the universe might end in a big rip where space tears itself apart. Or, if dark energy suddenly stops acting, we might end up with a big crunch into a giant ball of nothingness. But if dark energy stays constant, as current evidence suggests, heat death. The long cold silence, every structure you see, every star, every planet, every living thing exists because energy flows from hot to cold. When there's no more hot and cold, when everything is the same tepid nothing, the movie ends, not with a bang, not with a whimper, not with end credits. It will be an absolute silence. But here's what keeps me up at night as an engineer. I've seen this before, not in the cosmos. In code. Entropy, the force driving the universe toward its final silence, behaves exactly like something I've fought my entire career. Technical debt. Welcome back to Code, Cosmos, and Chaos, where we drag the biggest questions of existence into the harsh light of a code review. I'm your host, Chris. Last episode, we explored Q-Day and the coming quantum apocalypse for cryptography. Today, we're going bigger. Much bigger. We're talking about the ultimate system failure. The one that's going to take down, well, everything. The second law of thermodynamics. Entropy. The arrow of time itself. Arthur Eddington, one of the greatest physicists of the 20th century, once said that if your theory disagrees with the second law of thermodynamics, there's no hope. Your theory will collapse in deepest humiliation. That's how fundamental this is, and today I'm going to show you why it looks suspiciously like the thing that kills every software project eventually. Before we dive into entropy, let me take you back to the 1800s, because understanding how we discovered the second law tells you a lot about what it means. The Industrial Revolution was in full swing. Steam engines were transforming civilization. And engineers had a very practical question. How do we make these engines more efficient? How do we get more work out of less coal? A young French engineer named Sadi Carnot tackled this in 1824. He wanted to understand the theoretical limits of engine efficiency. What he discovered would become one of the most important insights in all of physics. There's a fundamental limit to how efficiently you can convert heat into work. You can't do better than a certain maximum no matter how clever your engine design. Why? Because some heat always has to flow to a cold reservoir. Always. It's not an engineering limitation, it's a law of nature. Then came Rudolf Clausius, a German physicist in the 1850s. He formalized what Carnot had intuited. He invented the word entropy, from the Greek for transformation, and gave us the second law in its modern form. The entropy of an isolated system never decreases. Ludwig Boltzmann, an Austrian physicist who became one of the founders of statistical mechanics, took it further in the 1870s. He connected entropy to probability, showing that entropy is really about the number of microscopic arrangements consistent with a macroscopic state. His famous equation, S equals K log W, where S is entropy, K is a fundamental constant now named after him, and W is the number of possible microscopic states, is carved on his tombstone. These weren't just theoretical discoveries, they were hard-won insights from engineers trying to solve practical problems. And they revealed something profound. The universe has a direction. Time has an arrow, and that arrow points toward decay. Okay, entropy. You've probably heard this word, you might even know it means something like disorder, but that definition is a little misleading. Let me give you a more useful way to think about it. Entropy is a measure of how spread out energy is. More specifically, it's about the number of ways energy can be arranged in a system. Here's an everyday example. Imagine you have a bedroom. A clean bedroom has low entropy, everything in its place. Books on shelves, clothes in drawers, bed made. There's basically one way for it to be clean. Now think about a messy bedroom. Books everywhere. Clothes on the floor, on the chair, half in the hamper. There are millions of different configurations that all qualify as messy. That's entropy in a nutshell. There are vastly more ways for things to be disordered than ordered. So if you let a system evolve randomly, it will almost certainly move toward more disorder. Not because the universe wants chaos, but because chaos is statistically overwhelmingly more likely. The second law of thermodynamics formalizes this. In any isolated system, entropy never decreases. It either stays the same or increases. Let's go back to that cup of coffee. When it's hot, the fast-moving molecules are concentrated in the cup. That's ordered, it's special. As the heat spreads into the air, those energetic molecules disperse. The energy spreads out into more and more possible configurations. Entropy increases. Now here's the crucial part. This process never reverses spontaneously. The air molecules around your coffee will never, ever spontaneously decide to donate their heat back to the cup. It's not impossible in the strictest sense, but the probability is so vanishingly small that you'd have to wait longer than the age of the universe to see it happen. And this is why entropy gives us something profound. The arrow of time. It's why we remember the past, but not the future. Why eggs break, but don't unbreak. Why people age, but don't unage. Entropy is the direction of time itself. Here's another way to think about it. Shuffle a deck of cards. The probability of getting any specific order, say all the cards in perfect sequence by suit, is astronomically low. But the probability of getting some random disordered arrangement? Nearly 100%. There are vastly more disordered states than ordered ones. That's entropy in action. The universe isn't conspiring against order, it's just that chaos outnumbers order so dramatically that disorder becomes inevitable. Now here's where my engineering brain started making connections. In software development, we have a concept called technical debt. It's the accumulated cost of shortcuts, quick fixes, and we'll clean this up later decisions. Every code base has it. Every single one. When you start a project, the code is clean. It's elegant. You understand every line. Low entropy, if you will. Then you add features. You fix bugs under deadline pressure. You hack in workarounds because the proper solution would make the marketing team lose their grip. A developer who understood a critical module leaves the company and their knowledge leaves with them. The code gets messier, more complex, harder to understand. The number of ways the system can be broken vastly exceeds the number of ways it can be working. Sound familiar? Technical debt is entropy. And just like entropy, it never decreases on its own. Left alone, codebases don't spontaneously get cleaner. They don't refactor themselves. Dependencies don't update themselves. Documentation doesn't write itself. The only way to fight technical debt is to constantly invest energy, developer time, attention, resources, into reducing it. Refactoring, code reviews, paying down the debt deliberately. And here's the thing, even that isn't a permanent solution. You can slow the accumulation, you can temporarily reverse it in isolated components. But the system as a whole is always trending toward more complexity, more disorder, more entropy. Eventually, the debt becomes so crushing that it's easier to rewrite from scratch than to maintain the existing system. I've seen it happen countless times. I've participated in it. We've all watched massive projects get sunset because the code base became too fragile, too complex, too entropic to save. There's a concept in software called bit rot, the idea that code degrades over time even if no one touches it. Dependencies become outdated. APIs get deprecated. The environment changes around the code. It's not actively breaking, it's passively decaying. That's entropy. And there's Conway's law, which states that organizations produce systems that mirror their communication structures. As organizations become more complex and siloed, so does their code. More entropy, more disorder. More ways for things to go wrong. The universe has the same problem, except there's no one to do the rewrite. So what happens when the universe's technical debt comes due? Let me walk you through the cosmic timeline. And I'll warn you, the numbers get big, really big. Right now, we're about 13.8 billion years into the universe's existence. Stars are burning, galaxies are colliding, energy is flowing, things are happening. But the stars are burning their fuel. They're converting hydrogen into helium, then heavier elements, releasing energy in the process. That energy spreads out into the cosmos and never comes back. In about 100 trillion years, that's 10 to the 14th power, the last stars will burn out. No more nuclear fusion. The universe goes dark, but that's not the end. There are still objects, white dwarfs, neutron stars, black holes. And black holes, we've learned, aren't eternal. Stephen Hawking, the British physicist famous for his work on cosmology and black holes despite being diagnosed with ALS at 21, showed they slowly evaporate through a process called Hawking radiation, where quantum effects at the black hole's edge cause it to emit particles and lose mass over time. A supermassive black hole, the kind at the center of a galaxy, will take about 10 to the 100th power years to evaporate. That's a 1 followed by 100 zeros. The word for that is Google, which is also where Google got its name. After the black holes are gone, we enter what physicists call the dark era. All that's left is a diffuse gas of particles, photons, and leptons, drifting through an incomprehensibly vast, cold, dark space. The temperature of the universe approaches absolute zero. And here's the key. At this point, there are no more energy gradients, no temperature differences, no hot regions and cold regions. Energy is spread out as uniformly as it can possibly be. When there are no gradients, no work can be done. No computation can occur, no change is possible. The universe has reached maximum entropy, thermodynamic equilibrium. It's not dead in the sense of being destroyed. It's dead in the sense that nothing will ever happen again. Forever. Now, here's where it gets interesting. Because scientists aren't just accepting entropy as a given. They're probing its edges, testing its limits, and finding some genuinely surprising things. First development. In October 2025, physicists at the University of Stuttgart proved that the Carnot principle, one of the foundational laws related to entropy, doesn't apply the same way at the quantum scale. For quantum objects whose properties are correlated, heat engines can actually exceed the traditional efficiency limits. They're calling it correlated quantum machines beyond the standard second law. This doesn't break thermodynamics, but it extends it, showing that the quantum realm has tricks we're still learning. Second, in July 2025, an international team published what they're calling the second law of entanglement manipulation. They proved that quantum entanglement, that spooky connection between particles, can be reversibly manipulated, just like energy in an idealized thermodynamic system. It's a quantum equivalent of the second law, and it deepens our understanding of how information and entropy relate at the fundamental level. Third, and this one fascinates me, in February 2025, researchers from Nagoya University tackled Maxwell's demon, that famous thought experiment where a hypothetical creature could sort fast and slow molecules without expending energy, apparently violating the second law. Their work showed that while quantum mechanics technically permits loopholes where the demon could extract more work than it expends, every quantum process can still be designed to comply with the second law. The demon can't actually break the rules, but the fact that it theoretically could under certain quantum conditions is wild. And in December 2025, Professor Jose Maria Martin Olalla, I hope I said that right, at the University of Seville showed that the vanishing of specific heats at absolute zero can be explained purely through the second law. This potentially eliminates the need for a separate third law of thermodynamics. The second law might be even more fundamental than we thought. What all of this tells us is that entropy isn't just a simple countdown to doom. It's a deep structure that touches information, quantum mechanics, and the very fabric of reality. Fifth, researchers at multiple institutions have been exploring whether life itself might be a thermodynamic phenomenon, that living systems exist because they're exceptionally good at dissipating energy gradients. Physicist Jeremy England has argued that life emerges precisely because it increases entropy faster than non-living matter. We're not fighting entropy. We're entropy's most efficient tool. So here's the question that haunts me. If entropy always wins, why do we bother? Why do we refactor code we know will eventually be replaced? Why do we build structures we know will eventually crumble? Why do we create art that will eventually be forgotten? Relationships that will eventually end? Lives that will eventually stop? Here's the engineering answer. Because the game isn't about winning. It's about how long you can keep playing. Every time you refactor code, you're buying time. You're extending the useful life of the system. You're pushing back the heat death of your code base by another week, another month, another year. Life does the same thing. Life is an entropy fighting machine. We take in energy, we do work. We maintain our low entropy structure against the constant pressure of disorder. Every heartbeat is an act of defiance against the second law. We can't beat entropy, but we can delay it. We can create local pockets of order, a well-maintained code base, a loving family, a moment of perfect understanding between two people, even as the universe as a whole winds down. And there's something profound in that. The universe is dying, and it made us, these improbable, temporary structures, to notice, to appreciate the heat before it dissipates, to document the gradients before they flatten. Physicist Sean Carroll once said that the remarkable thing isn't that entropy increases. The remarkable thing is that it was ever low enough to increase from. The universe started in an extraordinarily ordered state, and we exist in the brief window where that order is unwinding into complexity before it finally flattens into nothing. We are the universe experiencing itself in the brief flicker between perfect order and perfect disorder. That's not nihilism, that's poetry. So where does this leave us in a trillion years? Numbers too large for human intuition. The last meaningful event will occur, and then nothing. Forever. But that's not our problem. That's a problem for beings so far in the future that we can't even imagine what they might be. Our problem, our beautiful, temporary, meaningful problem, is what to do with the brief window we have. The window where energy can still flow, where work can still be done, where love can still be felt, and code can still be written, and questions can still be asked. The universe is winding down, and that's exactly why every moment of order, every pocket of meaning, every act of creation matters. Because they won't last forever. Because nothing will. And that's what makes them precious. I sometimes think about the engineers who built the first steam engines. They were just trying to pump water out of mines. They had no idea they were uncovering one of the deepest truths about reality. No idea that their practical problems would lead to equations that describe the death of stars. That's what engineering does. We solve immediate problems. And sometimes, in the solving, we glimpse eternity. Your coffee's getting cold. Maybe go drink it while it's still warm. Thank you for investing your precious low-entropy brain states into episode 4 of Code, Cosmos, and Chaos. If you're now looking at your messy desk and seeing the heat death of the universe, congratulations, you're starting to think like a physicist. Subscribe wherever you get your podcasts. Leave a 5-star review if you've accepted the inevitable. 1 star if you're still in denial. I respect both approaches. Hit me up on X at CodeCosmosChaos. What's the most elegant system you've ever seen slowly succumb to entropy? What keeps you fighting the second law? Let's contemplate the void together. Next episode, we're asking one of the biggest questions in all of science. Where is everybody? Fermi's paradox and the Great Filter? Why, in a universe this vast and this old, we seem to be alone. And what if the answer is that civilizations inevitably create something that destroys them? This is Chris, logging off from somewhere deep in the stack. Until next time, keep fighting the entropy, even though you already know how it ends.